Hey guys, thank you for having me here. I am a DevOps engineer at NS1. Only been working for about 6 years, so I'm pretty much a newcomer into this space. So again, thanks for having me here, and I hope I can give you guys something new to chew on with regard to software-defined networking. Closer? Yeah, better? Yep. Thank you. All right. So I'm just going to get started here. Software-defined networking. It's this thing that kind of sprouted out of Docker networking. It's been around probably since the dawn of networking in terms of virtualized anything, really. And it's becoming very prolific and a cause of a lot of heated debate among most of the networking community at large. A lot of people love it, a lot of people hate it, a lot of people don't understand it and don't even care about it at all. And I think that that's interesting because there's really no getting away from it at this point. Docker has become deeply rooted in our systems. Pretty much every enterprise I know is at very least testing it. And no matter what you think, it can help you. But the key to it is that it's a tool. And it's relying upon all the technology that most of you use every single day. It has been in your infrastructure since day one. Every single one of your switches, every single one of your routers, they all have the same technologies the software-defined network uses and relies upon. That being said, it's all about configuration management. It does a lot of the same things that Ansible or Chef or Puppet will do for your team, but it's specific to networking. It's going to take the configurations that a lot of you guys have been applying manually or applying with general scripts and making that all automatic for you. And one of the things that, one of the things I wanted to point out from the beginning is that it's designed to run on commodity hardware. This means that you can run this on a server, you can run this on a VM, you can run this on inside of a Docker container if you wanted to as well. This is one of the best parts about a software-defined network. It bridges the gap between needing to worry about having hardware, needing to worry about different versions, needing to worry about operating system compatibility, and abstracts that all away from you. And this brings kind of to the question of how does it work? As I said, it really relies on all the technology that you use all the time. And there are really two modes that they operate at this point, either within the kernel or on user LAN-based networking. So in kernel-based networking, you're going to talk VXLAN, you're talking routing tables, or clever elusive BGP. User LAN, you're talking a ton or tap device. This is stuff that VPNs have been built on top of for quite some time. And they both have their pros and their cons. The biggest pro and con of both of them is that they give you incredible configuration and flexibility in terms of how you want to set up your network. Their biggest con is they're slow. There's nothing that anyone can say about it. They're never going to outpace a hardware-based router or a hardware-based switch. It's just not going to happen. But what you need to weigh is the difference between being able to set up one configuration and have that propagate throughout your entire network all automatically without you having to lift another finger versus having 10 gigabit Ethernet connect all of your infrastructure. And that brings me to one thing that I wanted to point out. While they're slow, they aren't going to necessarily hold you back. You can easily support the vast majority of your use cases. But if you do need that 10 gigabit networking, you need to make sure that this is probably not going to be what you want. No matter what, they're probably not going to get you there. Not a single software-defined networking application I know of can actually support 10 gigabit, but you'll definitely be able to support 1 gigabit. And I find that most applications can rely on that just fine. The biggest key to how a software-defined network works and what makes it stand apart from the vast majority of the technology that exists today, think IPsec, point-to-point, L2TP, what have you, is the fact that it relies on a key value store that's distributed, and the key being distributed. So by using something like etcd or console, or using one of these new technologies, you're going to be able to automatically configure your network on the fly. And this is how it really relies on this is what it really relies on to enable that automatic additional or remove of any server or service that you add to your systems. This is really kind of what they came about to do, though, and why you would want to use one. It's all about reducing costs, reducing your complexity, or at least hiding the complexity, and accelerating your network team and operations teams. Because as we all know, as the containers get more and more, used and heavily spread out over the world. You have thousands, tens of thousands, hundreds of thousands of containers. And there's nothing that you're going to be able to do about it. It's going to get more and more, most likely, especially in the future. So being able to manage these networks in a very automatic way is becoming more and more crucial. So they reduce costs by basically reducing the need to have lots of hardware sitting around, most of the time not being used. Reduce complexity by, again, hiding away configuration, making it easier to set up that IPsec tunnel between all of your different gateway routers. All of a sudden, you can set up one piece of configuration, and every single one of your gateways on all of your different data centers or your co-locations are automatically configured, and you can talk to all of your nodes with ease and simplicity. And because of that, you actually allow your network and operations teams to do things that are more important to your company, by either allowing them to focus on figuring out the best way to set up your anycasted addressing, or figure out how to best set up your BGP to enable your clients to have lower latencies, instead of worrying about setting up these tunnels and setting up all this information that's really just tedious grunt work. Which brings me to the state of all of SDNs right now. Really, it's unfortunate, but there is way more marketing and buzzwords and a ton of money being poured into flashy websites than there is the actual technology at hand. And really, it's, at this point in time, heavily dominated by three technologies. You're talking Calico, you're talking Weave, and you're talking about Flannel. They are definitely the most well-known. They're the most used. I'd say Calico is probably taking the lead on top of what maybe Flannel, and then Weave being like a close follow behind both of them. They all have their own pros and cons. They range in functionality from very simple configuration of UDP encapsulation to something like Calico, which will allow you to do group management, set up BGP routes, and actually manage your IP table rules on the fly across your entire cluster. They have great functionality, but there's very little that can really be said that makes them the same, other than, again, that key value store that allows them to propagate your changes of your network across the world very simply. Which actually brings me to some of the clear triumphs. They nailed it when it came to configuration management. Pretty much every single one of them is going to give you that ease, give you that simplicity that you wanted, and allow your teams to focus on other things once that initial configuration is done. And this has really enabled a lot of teams and a lot of different companies to compete with bigger companies that have these massive networking teams and a ton of money to pour into their networking operations, so that they can just eke out as much performance as possible, where these small companies use an open source technology and now they're competing, which is a really interesting thing, and it's really kind of changing the landscape a little bit, especially when it comes to distributed applications. And while it's doing a really good job, it's also falling short in a lot of ways. The first and foremost is that everything is really focused on inter-LAN connectivity. And most of the time, you're going to see a lot of SDNs set up on a cluster of 100 nodes within a single data center that you're connecting 2,000, 3,000 containers, but it's all within one data center. And every single one of those containers gets a unique IP address, even though the vast majority of the time, those different containers don't require an IP address at all. So you end up having a bunch of overhead, creating these networks, managing these networks, using up massive numbers of IPs, when in reality, you needed 3 or 4 IPs to manage your public-facing network. And then you could have had the same IP with different ports used to manage all the APIs behind a load balancer, what have you. These kind of things are not necessary, and they cause a lot of problems when you try to switch a container from one data center to another, or from one cluster to another. It adds a lot of overhead, and it adds a lot of worry about making that configuration change as it goes through. The biggest thing, especially for my company, was the lack of support for hybrid deployments of IPv6 and IPv4. The vast majority of the time, you get one or the other. Certain technologies have been making massive strides towards supporting fully hybrid setups, but as everyone knows, there's no easy way to switch entirely from IPv4 to IPv6. It's just a fact of life right now. There's still a ton of applications out there that just straight up don't support IPv6, and you need to be able to support both. So this is something that I found very interesting, considering it's a networking technology and the massive focus that IPv6 has been in the network community at large very recently, and will be for the next foreseeable future. Which leads me to quantum. And this is a technology that was built out of the needs for NS1. And because of the shortcomings of some of the current tech that's out there, it is specifically designed and built to be open source, extendable, and easily maintainable. And it's fully single static binary that's super easy to work with. The idea was to build something simple, get it out the door, and build on top of it, and build a framework so that we can actually add more functionality down the road. And it had a few key challenges that we needed to solve for it to be viable in NS1 and to be viable in networks at large. First and foremost is that globally distributed infrastructure needs to be the key. NS1 has hundreds of servers spread out literally over the world, and I'm sure that's the same case for a lot of the people here. We have big networks, we need to manage these networks easily, and the more we grow, the bigger our networks become. So getting something that manages your network over the entire globe is not really something that any of the current software-defined networks could do at the time. So other than that, as I just said, we needed to be able to support a fully hybrid system. There is no doubt about it. We have a lot of IPv6, pretty much all of our servers have it, but there are certain locations in the world where we just couldn't get our ISP providers to give us IPv6 access. We had to be able to support IPv4 only systems at the same time as supporting IPv6 only systems. So this is something that Quantum needed to be able to do. And we wanted to, again, make it very extendable. So it allows for injecting middleware. So if you need compression or you need encryption, you can inject that into Quantum so that at your network layer, you have compression or encryption without having to worry about managing TLS certs over every single one of your applications. You don't have to worry about setting up gzip on your load balancer to your API. It's done automatically at the network layer. You don't have to worry about these things anymore. And one of the biggest things that I wanted to do specifically when building Quantum was focus on host networking versus container networking. This works really well at NS1 because of our sys setup. We only run network host. If any of you guys here have used Docker, you'll know what that means. But essentially what it means is that we don't use virtual networking when it comes to our containers. Every single one of our containers is directly hooked into the host networking, and we manage everything on the host. This is due to our nature. We're a DNS company, so we need that raw performance. So what we didn't have, though, is what we wanted was an SDN to manage our management of these servers. Instead of having to worry about binding ports or actually breaking out of that network jail, we just wanted to be able to say this other IP on our host, this is where your net management comes from, and then the other actual public IP is where all your DNS traffic or all your API traffic is going to be coming from. Some of the successes, as I just said, is the pluggable interface. We can, at will, change the backend networking technology. If we want to use a TUN device, we can use a TUN device. If we want to use a TAP device, we can use a TAP device. If we want to set up a UDP socket on the back end, we can. If we want to use a DTLS socket based on OpenSSL, we can. And it is fully designed to be global. It can handle network partitions. We can lose access to half our infrastructure and the network continues to work. And what I mean by that is just because there's a partition and it can't talk back to our master clusters of our key value store doesn't mean it's going to all of a sudden break. Those containers and those servers can continue to talk, which is crucial for us, obviously. And the last real thing is that it ensures that the hosts are 100% the primary focus. This comes with a caveat, unfortunately, which is there is no support for Docker networking at the moment. If you want to use a network plugin, you're not going to be able to. This is unfortunate, but just kind of a fact of time and personnel constraints. It started as an open source project. It will remain an open source project, but it is still just that. I only have so much time to work on it. There's only so much work time in the day. So there have definitely been some other trade-offs. Most importantly is the trade-off between developer speed and raw performance. Instead of writing this in C or C++, where it would have had the most possible performance to get every bit through it faster, it's written in Golang to increase just the development speed and performance there. Get it out the door, get an idea of the functionality we needed, what we wanted, what we didn't need, and then move on, get back to performance when we had the time. Unfortunately, while you can inject plugins, you do have to compile Quantum to get those in there right now. This is an unfortunate deal, but plugin functionality in Golang is finally a real thing, and we'll be coming back to that very soon to get that full dynamic injection working like we really wanted it to from the beginning. And then one last real trade-off that's unfortunate, especially for you, those of you that aren't using etd or would want to use something like this, is that it is got a hard dependency on CoreOS's etd. This is unfortunate just because it means that we don't have as much flexibility in terms of the configuration that you'd want to be able to use potentially. And then last and not least, Linux only. Unfortunately, Windows is probably never going to happen, but hopefully BSD, Solaris, these other types of Unix type of operating systems will definitely be supported. But for now, a lot of the Linux kernel is where Quantum lives and didn't have time or the hardware to test it on anything else, which brings me to the future of this technology and kind of where it hopefully will continue to deviate from the standard put in place by Flannel and Weave and Calico. We're going to integrate some of the features of these other technologies. We want that full group and host support. We want to be able to basically say, if you're part of this group, you only can talk to this other group, just like Calico can do. And we want to focus on that raw performance. That's the thing that I want to point out the most, is that it isn't going to be nearly as fast as your standard Flannel using VXLAN, but it'll give you more flexibility than your VXLAN with Flannel would be. And that's something that we want to get back to, and we'll most likely be moving the most critical performance pieces into C or C++ to make that just that much faster. And then obviously support for BSD, because we need to be able to support the better networking kernels that exist out there. And then maybe, just maybe, have support for Windows in the future if I can get some help for it. But that's really Quantum, and I guess the real thing I wanted to point out is it's different because it doesn't rely on the idea of containerized networking. It will give your hosts what you want to give your containers, and it goes against the anti-pattern, or what I believe is an anti-pattern, which is every container getting a unique IP address. And that's really kind of my talk. So thank you for bearing with me and listening to what I had to say, but does anyone have any questions?
There's a question out there.
Questions? Okay, go ahead.
So, this is more, what usually drives, like, when people talk about network container, it's like ideas, and there's different people who say different things in that. What usually drives that requirement in your mind? When people approach you with that type of question?
What I find usually drives the idea of having a unique IP address for each and every one of your containers is people wanting the idea that a container is a VM. When I talk to a lot of people about containerization and what a Docker container is, the first thing they say to me is, oh, it's just like a VM, but it has a lighter weight hypervisor. And that's really not the case, at least not in my mind. And I don't believe that was the idea of going forward with containers either. So when people think of Docker networking, they're just like, oh, it should be like my hypervisor, VMware, Citrix, what have you, and it should be able to give this container a full networking setup, a full, entirely its own kernel, which definitely doesn't happen. And have that level of isolation between the other containers to make it a virtual machine. And I find that that's really where that idea came from, but that could just be my misunderstanding of the situation.
Yeah, Christian, I know you guys, you developed your own SDN network. So companies that don't have the resources, the software development team, what do you recommend to them in selecting their vendors that can provide the software-defined network carriers, for example?
Fair enough. If you don't have a development team and you don't have that infrastructure in place, it makes sense to kind of weigh your options and what exactly it is you need from a software-defined network. I find most people use it because it's a buzzword and they're like, oh, it goes with Docker. Vast majority of the time, if you don't have a globally distributed infrastructure or you don't have infrastructure that's changing every day or by the hour or by the minute even, it may not make sense in your network. If you do though, take a look at Calico, take a look at Flannel. They are amazing tools. There's nothing wrong with any of those technologies by any means. They work extremely well. For instance, if you need that encryption on every single packet, take a look at Weave. It works very well. It is a little slow, but that's what happens when you introduce encryption to every single packet leaving your system. Calico is probably the most mature at this point, other than Flannel, although Flannel's gotten a little segmented because of all the different types of plugins it has. I would definitely suggest taking a look at all three technologies, and if not, maybe you can get away with just using a standard bridge network in your Docker systems, if you need that kind of configurability. I hope that answers your question.
No, no, no.
What was the use case at NS1 for containers kind of to begin with?
The use case for containers at NS1 was all about encapsulation of, well, dependencies, really. We needed to be able to easily manage the version of all the dependencies of our software, and that was incredibly easy to do within a Docker container. In reality, we use containers very similarly to using an old school chroot jail, where we just kind of have a specific root and it works great. And that's all the technology we use out of Docker, really. The best part about it for us is the actual distribution aspects. We can download a new container after building it in our CI/CD platform, and we can distribute that across the world incredibly fast and incredibly easily just by doing a Docker push and then a Docker pull. So our use case is really just about dependency management.
Any other questions? Okay, thank you.
Thank you, Christian from NS1. Thank you to everyone for coming. We're going to go to 10 o'clock. Join us in the back for food, drinks, beer on the rooftop. It's nice and cool out there. You get to watch the sunset on one of the longest days of the year. And we'll see you back at the next event in September. And thank you to all our sponsors again. Thank you.